everyone. My name is Tarisa Ross, and I have the honor of participating in the National Society of Black Physicists Scholars Program with Princeton University and the Simons Observatory to build the Universal Shorts Diagnostic Code. This was done under the advisement of Suzanne Staggs. My direct advisor is Aaron Healy, and Zach Adkins helped a lot with the code. So without further ado, let's begin. So this is the detector module. The detector module is basically, we're looking at the overview of the situation before we get into the Universal Diagnostics Code. So the detector module has about 2,000 transition S sensors that pick up the sky signals between frequencies of 25 to 290 gigahertz. It was implemented to be used in Simon Observatory telescopes, the large ones and the smaller aperture telescopes. And there's about 80 detector modules in total that the Simons Observatory will produce. And there needs to be reliable assembly procedures, including building tools that facilitate the assembly procedure. So before we get into the meat of the problem, gotta look at the generalization of the issue. So we have these, this expansion of these shapes being shown in the top left corner of the screen. What we're going to do is focus more on one of those wafers in the next slide, and then the bottom right is basically just it in real life, and the top is just, a representation that's drawn. So to look closer at the actual issue, let's zoom in on the actual wafer, and we have the design right in front of us. So the wafers themselves are made from silicone, and metal wiring is fabricated on top of it. And on each wafer there are circuits, and they're electrically connected through wire bonds. Due to them being so densely packed, there's about 2,000 detectors on a 100 millimeter wafer. It keeps shorting out. So, before the Universal Diagnostics Code was conceived, before the issue was fixed by, a short popping up in between these electrical lines, as you can see in the top picture. And, since we didn't know how to triangulate the actual location of the short, we just be generally an issue in a general area. So then you'd have to pull out 300 wire bonds at a time to take care of the short, and then replace those wire bonds later on, which would be time consuming, it damages the equipment, and it's just not a good strategy overall. So this is why the Universal Diagnostics Code was conceived. So basically the code is used to triangulate the location of the actual short using linear algebra and algebra on the DC wafer. To do this, to create this code, we use layout editor to measure the circuits. You can see on here, because there's a lot of wires just running up and down it. And then we use Python to actually implement the code as the language that we use. So to get a better idea of how to solve this issue using linear algebra and algebra, we have to pull up the schematics of the issue. So when you look at the previous slide at the top, you had these lines going down. This is basically a representation of those lines in a more simpler idea. So imagine we have two, wire bonds running parallel to each other, and there's a short somewhere between them. We can figure out where the short is through a system of equations. So we have BL1 plus BL1 minus BL2 plus BL2 minus. If you go from BL1 plus to BL1 2 minus, that's a whole different direction than just going straight across, which is a part of the system of equations that's being represented in here. So at the end of, figuring out where the equations are, we have 5 equations and 5 unknowns, which can be represented, using linear algebra. So basically having them connected, the shorts basically represent the resistance drop that's going to be between the two lines. And we can use the schematic. We use these schematics to simplify the situation to figure out how to solve it. And the last step to figure out where the short is, to triangulate the location using this method, because we don't know where the shorts are, but we do know which lines are being affected. So now we have the code that we actually use to implement in this project. So it's built from three basic structural files. We have the wafer database that stores the trace information, so that includes like the length of each bias line, what bias line we're using, because there were about seven that we were referencing to, and then every trace segment, meaning every time it turned, that would be a new segment that would need to be measured. We also have the module that defines all the system objects and mathematical functions. So this includes, the linear algebra we use. That includes finding the resistance measurement that we calculated, and then the script that demonstrates the use of this module. So, at the end where it basically displays where the short is, or where it's going to be through, triangulation. So as you can see in the bottom left screen, there's code in Python and Spider, and it's basically displaying what kind of uh, what kind of um, functions we used in Python, and we use that to output the graph at the top, which displays the actual location of the short. So the blue line itself represents the bias line, which is, a giant line segment on the DC wafer. And then we have the blue lines, the blue dots. The blue dots themselves represent the every time it changed directions. And then the two cyan dots represent the actual short. So our next steps in this project, so we focused this part of the project on the DC wafer, and the next part of the project would focus on the RF wafer and the detector wafer. The RF wafer is more of a 3x3 matrix, so that would be a little easier to work with. But as we decided in this project, obviously seeing that, we decided to do something harder and then move to something that would be a little easier for us to understand. We're doing the easy second and the hard first. So right now at this moment, groups in the Simons Observatory are definitely using this code to figure out, the trace segment lengths, how long bias lines are, to calculate resistances. This is definitely being used right now within the Simons Observatory. As it's been written, as it is right now, this code wasn't just used for our particular situation. It can be used for other situations that has high resistivity circuits and densely packed, circuits running alongside each other that could have shorts just as ours did. So I learned a lot from this project. Coding was something I was not very good at before I started this. I had a couple of classes that used it just for like understanding mathematical equations, but it really solidified my knowledge by being a part of this internship. I learned how to problem solve. So at the beginning of this internship, I had the idea of possibly using temperature to figure out exactly where the shorts could be. But after a while, after going through the internship, realizing that that would be a little more difficult and could be a supplemental to the code, because the resistance drops are such a minute factor in the actual position of where the shorts are. So it wouldn't really be helpful unless you knew kind of where the shorts were at, which is why it would be a supplemental to the actual universal diagnostic shorts code. E&M wasn't something I was very good at in my undergrad. So, learning more about, circuitry and all of those things really helped me understand it more. And I also learned a lot about linear algebra, which is something that also wasn't required for my degree, but it was something that we did learn a little bit about alongside of a bunch of other mathematical concepts. So it became really, really useful to my understanding, especially when I got to implement it in a real world situation. I'm really grateful for this opportunity, and thank you so much.